Hello everyone, and welcome to day 1 of our Data Science and Machine Learning course. My name is Vikas Gautam, and I'll be your instructor throughout this training. Over the next several sessions, we'll build a strong foundation in data science, machine learning, and artificial intelligence. We'll begin with the basic concepts and gradually move towards more advanced topics, including data preprocessing, visualization, machine learning algorithms, model evaluation, and practical implementation using Python. This course is designed to be hands-on. Along with understanding the theory, we'll work through real-world examples and coding exercises so that you gain practical experience that can be applied to projects and interviews. Today's session is focused on building a good understanding of numpy arrays are, why they are important, and how they are used. By the end of today's class, you should have a clear understanding of the material covered. So let's get started with our exciting journey into the world of data science and machine learning.
Now that we've completed the introduction, let's take a look at the agenda for today's session. Today's primary focus will be on numpy, which is one of the most important libraries in Python for data science and machine learning. Before we begin building machine learning models, it is essential to understand how data is stored, manipulated, and processed efficiently. NumPy provides powerful data structures and mathematical operations that make these tasks fast and convenient. Throughout today's session, we'll start with the basics of NumPy and gradually move on to creating arrays, understanding different data types, performing mathematical operations, indexing, slicing, reshaping arrays, and using built-in statistical functions. We'll also work through several practical examples so you can see how NumPy is used in real-world data analysis and machine learning projects. By the end of today's class, you'll have a solid understanding of NumPy and be comfortable using it in your own Python programs. So, let's begin by understanding what NumPy is and why it has become the foundation of almost every data science and machine learning project.
Before we start writing any Python code, we need to set up our development environment correctly. The first software we'll install is Anaconda. Anaconda is one of the most popular Python distributions used by data scientists because it comes with Python, Jupyter Notebook, and many useful libraries already included. This saves us a lot of time compared to installing each package separately. Next, we'll install the latest version of Python if it is not already included in your Anaconda installation, or if you prefer to have a standalone Python installation. Having the latest stable version ensures compatibility with modern libraries and features. Once the installation is complete, open the Start menu and launch Anaconda Navigator. This provides a graphical interface from which you can easily launch Jupyter Notebook, Spider, or other development tools without using the command line. From Anaconda Navigator, click the Launch button under Jupyter Notebook. Your default web browser will open the Jupyter interface, where we'll write and execute all of our Python programs throughout this course. In Jupyter Notebook, you can create a new notebook, write code inside individual cells, and execute each cell independently. This makes it very easy to experiment with code, test ideas, and visualize results step by step. If you need additional code cells, simply click the plus button or use the Insert menu to add new cells. After writing your code, press Shift plus Enter to execute the current cell and move to the next one. One of the biggest advantages of Jupyter Notebook is that you can combine Python code, explanations, equations, images, and charts in a single document. This makes it an excellent tool for learning, experimenting, and documenting your work. Once everyone has completed the installation and successfully opened Jupyter Notebook, we'll begin our first NumPy program and start exploring Python for data science.
Now that our development environment is ready, let's understand an important concept in Python: libraries and packages. Python comes with many built-in features, but for specialized tasks such as data analysis, machine learning, visualization, and scientific computing, we use additional libraries. A library is a collection of pre-written code that allows us to perform complex tasks without writing everything from scratch. Think of a library as a toolbox. Instead of building a hammer or a screwdriver yourself, you simply pick the right tool and use it. Similarly, in Python, we import libraries that already contain tested and optimized functions. Before we can use a library, it must first be installed on our computer. This is usually done only once. For example, to install NumPy, we use the command pip install NumPy. This command downloads the NumPy package from the Python package index and installs it on your system. Once the installation is complete, we can import the library into our Python program. The most common way is import NumPy as NP. Here, NP is an alias, or a short name for the NumPy library. Although you can use any alias, NP has become the standard convention used by Python developers, data scientists, researchers, and machine learning engineers around the world. Using this convention makes your code easier for others to read and understand. After importing the library, it is a good practice to verify that the installation was successful. We can do this by checking the installed version using print.np.version. If a version number is displayed, it confirms that NumPy has been installed correctly and is ready to use. From this point onward, we'll use the NP alias throughout the course whenever we work with NumPy. You'll see it repeatedly in our examples, exercises, and projects. In the next section, we'll begin creating NumPy arrays, which are the core data structures used for efficient numerical computation and form the foundation for many machine learning algorithms.
An array is like a flat one-dimensional list with elements, though it can be more than one-dimensional. The main difference is that arrays are usually fixed in size and type, e.g., all elements must be integers, while lists are more flexible and can store elements of different types. Now that we've learned how to import the NumPy library, let's look at one of its most important features, the NumPy array. Before NumPy, Python programmers primarily used lists to store collections of data. Lists are simple, flexible, and easy to use. They can hold different types of data, such as integers, floating point numbers, strings, and even other lists. For example, a Python list could contain the values 10, 25.5, machine learning, and true, all in the same list. This flexibility is useful in many situations. However, when we work in data science and machine learning, we often deal with large data sets containing thousands or even millions of numerical values. Performing calculations on standard Python lists can become slow and inefficient. This is where NumPy arrays become very useful. A NumPy array is a specialized data structure designed for fast numerical computation. Unlike a regular Python list, a NumPy array is intended to store elements of the same data type, such as all integers or all floating point numbers. This consistency allows NumPy to optimize memory usage and perform calculations much more efficiently. Another important point is that NumPy supports one-dimensional, two-dimensional, and even multi-dimensional arrays. These are essential for representing vectors, matrices, images, and data sets that are commonly used in machine learning. Let's create our first NumPy array. First, we import the NumPy library using the standard alias import NumPy as NP.
Next, we create a one-dimensional array using the array function and pass a list of numbers as input. Finally, we print the array using print command. When you run this program, Python displays all the elements stored in the array in the same order in which they were created.
Before we continue working with numpy arrays, it's important to understand Python lists because numpy arrays are often created from lists. Let's first talk about comments in Python. A comment is used to explain the purpose of our code. Comments are ignored by the Python interpreter, so they are meant only for humans reading the program. We create a single-line comment by placing the hash symbol or pound symbol before the text. Writing meaningful comments makes your code easier to understand and maintain, especially when working on large projects or collaborating with other developers. Now let's move on to Python lists. A list is one of the most commonly used data structures in Python. A list is an ordered collection of items enclosed within square brackets. Unlike numpy arrays, a Python list can store different types of data in the same collection. For example, in this list we have an integer, a string, a floating point number, a Boolean value, and another string. List equals 1, hello, 3.14, true, string. This demonstrates the flexibility of Python lists. They are capable of storing heterogeneous data types, which makes them useful for general-purpose programming. If we use the print function, Python displays all the elements of the list in the same order in which they were stored. Besides lists, Python provides several other built-in collection types. A tuple is similar to a list, but it is immutable. This means that once a tuple is created, its contents cannot be modified. Tuples are useful when the data should remain constant throughout the program. Another important collection type is the dictionary. A dictionary stores data as key-value pairs, allowing us to retrieve information quickly using a unique key. Dictionaries are widely used to represent structured data, such as employee records, customer information, or configuration settings. As we progress through this course, you'll learn when to use lists, tuples, dictionaries, and numpy arrays. Each data structure has its own strengths, and choosing the right one is an important programming skill.
NumPy stands for Numerical Python. NumPy is a Python library used for working with arrays. In Python, we have lists that serve the purpose of arrays, but they are slow to process. NumPy aims to provide an array object that is up to 50 times faster than traditional Python lists. NumPy arrays are stored at one continuous place in memory, unlike lists, so processes can access and manipulate them very efficiently. This behavior is called locality of reference in computer science.
Please note the type or dtype function to know the data type and range function, which starts from 0 to n-1, where n is the number specified in the bracket. We can use range function and therefore loop statements like variable I from 0 to 9. As for I, in range open parenthesis 10 close parenthesis. Also note that indentation is very important in Python, which is 4 spaces or 1 tab below each function declaration. In this section, we'll learn how to access elements from a numpy array using indexing. Indexing is one of the most fundamental concepts in Python and NumPy because almost every data manipulation task depends on it. Python uses zero-based indexing, which means the first element of an array is stored at index 0, the second element at index 1, and so on. If an array contains n elements, the last element is always located at index n-1. For example, let's create a one-dimensional numpy array. If we want to access the first element, we write print open parenthesis arrow open bracket 0 close bracket close parenthesis, similarly r open bracket 1 close bracket returns the second element, r open bracket 2 close bracket returns the third element. Now let's look at a two-dimensional array. We can create one using the arrayNgos function together with reshape. For example, a 2 equals n p dot arrange 15 start.reshape3 4, the arranged function, generates a sequence of numbers from 0 up to, but not including 15. This produces 15 numbers in total. The reshape open parenthesis 3, 5 close parenthesis function then organizes these numbers into 3 rows and 5 columns. The resulting array looks like this. Notice that reshape does not change the data. It only changes how the data is arranged. Next, let's understand the len function. When we write len a2, the output is 3. Len returns the size of the first dimension. Since our array has 3 rows, the result is 3. If we want the complete dimensions of the array, we'll later use the shape attribute, which returns both the number of rows and columns. We can use negative indexing to access an array from the end. If n is the length of an array, then we can use n-1 and -2 to access the last element or last, but one element, print the last element from the second row, AR. Open bracket, 1, -1, close bracket, close parenthesis. So far, we've learned how to access array elements using positive indexing, where counting starts from the beginning of the array. Now let's learn another powerful feature of Python and NumPy called negative indexing. Negative indexing allows us to access elements starting from the end of an array instead of the beginning. This is especially useful when we don't know the exact length of the array or when we're interested in the last few elements. The indexing starts from -1. The index -1 always refers to the last element of the array, -2 refers to the second last element, -3 refers to the third last element, and so on. Let's look at an example. The output is 9. Similarly, AR open bracket 0, -1 close bracket returns 4, which is the last element of the first row. AR open bracket 1, -2 close bracket returns 8, which is the second last element of the second row. Notice that negative indexing works exactly the same way in one-dimensional arrays, two-dimensional arrays, and even higher dimensional NumPy arrays. Negative indexing becomes extremely useful in real-world programming. For example, if you're working with stock prices and want the latest closing price, you can simply access the last element using index -1. If you're analyzing time series data and need the previous day's value, you can use index -2 without worrying about the total length of the dataset. Now that we know how to access a single element using indexing, let's learn how to access multiple elements at once using slicing. Slicing allows us to extract a portion of an array without modifying the original array. This is extremely useful when you want to work with only a subset of the data. The basic syntax for slicing is array start end. Here, the start index is included in the result, but the end index is excluded. This is one of the most important rules to remember in Python. Slicing in Python means taking elements from one given index as start up to another index. We pass slice instead of index like this, start end. We can also define the step like this, start at end step. If we don't pass start, it's considered 0. If we don't pass end, it's considered as length of array in that dimension, that is the last element. If we don't pass step, it's considered 1. Let's understand this with an example. If we write our open bracket 1:5 close bracket, Python starts from index 1 and stops before index 5. Index 1 contains the value 2. Index 2 contains the value 3. Index 3 contains the value 4. Index 4 contains the value 5. Since index 5 is excluded, the output becomes 2, 3, 4, and 5. This explains why the end index is never included in the result. Now let's understand the complete slicing syntax. Start end step. The start tells Python where to begin. The end tells Python where to stop, but remember, it stops just before that index. The step determines how many positions Python should move after selecting each element. For example, if the step is 2, Python selects every second element. One of the best features of slicing is that all 3 parameters are optional. If we omit the start index, Python assumes the slice begins from index 0. If we omit the end index, Python continues until the last element of the array. If we omit the step value, Python assumes a step of 1, meaning every element is selected. Slicing is widely used in data science and machine learning. For example, we often split data sets into training and testing sets, extract specific columns, select rows that satisfy certain conditions, or retrieve recent observations from time series data. Slice elements from the beginning, index 0 to index 3, where index 4 is not included. Likewise, you can extract specific terms, form a string or match patterns, and then replacing it like changing, working to worked. Here we will find index where eng starts in the given word. Remove it or replace it with ed and add it at the end of work to become worked. Some string matching functions are contains like any, etc. For integers, we have equal to, not equal to, greater than or less than as, comparison operators which returns true or false as 1 or 0. Please note the difference between assignment operator and comparison operator. For example, variable ball equals 10 is an assignment operator. And if open parenthesis a equals b, close parenthesis, is comparison operator, which checks whether variable a is equal to variable b or not.
We can use the minus operator to refer to an index from the end. In the previous slide, we learned how to use slicing with positive indexes. Now let's extend that concept by learning about negative slicing. Negative slicing allows us to select a range of elements by counting from the end of the array instead of the beginning. This is very useful when we don't know the exact size of the array or when we simply want to access the last few elements. Just like negative indexing, negative slicing starts counting from the end. The last element has an index of -1. The second last element has an index of -2. The third last element has an index of -3, and this pattern continues. Let's look at the first example. We create a numpy array containing the values from 1 to 8. Now we write ARR -3 -1. Let's understand this carefully. The starting index is -3, which refers to the value 6. The ending index is -1, which refers to the last element. However, remember one important rule of slicing. The ending index is never included. So Python starts from the value 6 and stops before the last element. Therefore, the output becomes 6 and 7. Notice that the value 8 is not included because the ending index is excluded from the result. Now let's look at another example. Suppose we have the following array. If we write ARR 1, 5, 2, this statement uses all three parts of the slicing syntax: start, end, and step. Python starts at index 1, which contains the value 2. Then it moves 2 positions at a time because the step size is 2. So it selects 2, then 4, and stops before reaching index 5. The output is 2 and 4. This demonstrates how the step parameter allows us to skip elements while slicing. Negative slicing and step values are extremely useful in data science. For example, we often retrieve the last few records of a dataset, sample every second observation, or reverse an array to inspect recent values. These operations become very simple using slicing.
We can reverse the entire array in one step. Reverse the list. Reverse list equals list ::(-1). Starting from the end of the sequence, with a step of -1, moving backward through the sequence. If we have to refer to all the rows or columns, we can use : instead of indexes. So far, we've learned about indexing, slicing, and negative indexing. Now let's combine these concepts to perform a very common operation, reversing an array. In Python and NumPy, we can reverse an entire array or list using a single slicing expression. This is one of the simplest and elegant features of the language. Let's first create a simple list. Now suppose we want to display the elements in reverse order. One way would be to write a loop and traverse the list from the last element to the first. While that works, Python provides a much shorter and cleaner solution using slicing. We simply write reversed list equals list : -1. Let's understand what this notation means. The general slicing syntax is start, end, step. In this example, both the start and end positions are left empty. This means Python automatically considers the entire list. The step value is -1, which tells Python to move backward through the sequence instead of forwards. Because Python starts from the end and moves one position backward at a time, it returns the elements in reverse order. The output becomes 7, 6, 5, 4, 3, 2, and 1. Notice that the original list is not modified. Instead, Python creates a new reversed sequence. If you print the original list again, you'll see that it still contains the values in their original order. This same technique works with numpy arrays as well. Whether you're working with a one-dimensional array, a two-dimensional array, or even higher dimensional data, slicing with a negative step is a fast and efficient way to reverse the data. The slide also mentions the colon operator. In NumPy, a single colon represents all elements along a particular dimension. You'll use this frequently when working with rows and columns. For example, if we write array, -1, the first colon means select all rows, while -1 reverses the order of the columns. Similarly, array, -1, selects all columns while reversing the order of the rows. These operations are very common in image processing, data preprocessing, and machine learning applications, where reversing rows or columns is required before performing further analysis.
There, colon means select all rows or all columns as told earlier. It will start from first element, and with a jump of 2 steps end, at last step his is a test for the API of 11 labs.
Strings used to represent text data. The text is given under quote marks. Integer, used to represent integer numbers. Float, used to represent real numbers. Boolean, used to represent true or false. Complex, used to represent complex numbers. A data type tells Python what kind of value is stored in a variable or an array. Knowing the data type helps Python decide how to store the data in memory in which operations can be performed on it. Let's begin with the most common data types used in Python and NumPy. The first data type is the string. Strings are used to represent text and are always enclosed within single or double quotation marks. Examples include names, cities, product descriptions, or any textual information. For example, machine learning, Python. The next data type is the integer. Integers represent whole numbers without any decimal point. Examples include values such as 10, -5, 0, or 250. The third data type is the float, which is used to represent numbers containing decimal values. Examples include 3.14, 25.75, or 100.0. Floating point numbers are commonly used for measurements, percentages, temperatures, and scientific calculations. Another important data type is the Boolean. A Boolean variable can have only one of 2 possible values, true or false. Boolean values are widely used in conditions, comparisons, filtering data, and decision-making statements such as if and while. The final data type shown here is the complex data type. A complex number consists of a real part and an imaginary part. For example, 10 plus 2j, or 1.5 plus 2.5j. Complex numbers are commonly used in electrical engineering, signal processing, control systems, and scientific computing. Now let's see how NumPy identifies the data type of an array. We create a NumPy array containing only integers. To determine the data type, we use the dtype attribute, print.arr.dtype. The output is int32. This means that NumPy has stored each value as a 32-bit integer. On some systems, you may see int64 instead. The exact type depends on your operating system and Python environment. Now let's create another array containing strings. ARR equals np.array, apple, banana, cherry, donkey. Again, we print the data type, print.arr.dtype. The output is _u6.
Here, U stands for Unicode, meaning the array stores Unicode text. The number 6 indicates the maximum length of the strings stored in that array. Since banana contains Hex characters, NumPy allocates enough space for strings up to 6 characters long. Understanding data types is very important because they affect memory usage, computational speed, and compatibility with machine learning algorithms. Choosing the appropriate data type helps your programs run faster and use less memory, especially when working with very large datasets.
In this example, we will convert data type from int to string using function asType. New r equals r.asType of str. We can use built-in available functions provided by libraries, but if they do not fit the purpose, then we may have to write our own functions. 17.
Sometime we may need to modify the columns of data or create new columns or rows. Then we may keep the original table separate as backup, so that the original data, if needed, can be used later and create a new data table or array. The main difference between a copy and a view of an array is that the copy is a new array and the view is just a view of the original array. The copy owns the data, and any changes made to the copy will not affect original array, and any changes made to the original array will not affect the copy. The view does not own the data, and any changes made to the view will affect the original array, and any changes made to the original array will affect the view.
X equals array.copy. When we change the first element of array, see array is modified, but X, the copy, is not.
NumPy arrays have an attribute called shape that returns a tuple with each index having the number of corresponding elements, like the dimension size as rows, columns. Whenever we create a NumPy array, it is important to know its dimensions. The shape attribute tells us exactly how the data is organized. The shape of an array is returned as a tuple. Each value in the tuple represents the size of one dimension. For a one-dimensional array, the shape contains only one value, which represents the total number of elements. For a two-dimensional array, the first value represents the number of rows, while the second value represents the number of columns. Print the shape of a 2D array. Print arr.shape.
In this slide, we'll learn how to iterate through every element of a numpy array using the np.ndIterator function. The array shown here is a three-dimensional array containing 8 elements. Although the data is organized into multiple dimensions, there are situations where we need to process each element individually. NumPy provides the ndIterator function for this purpose. The name ndIterator stands for n-dimensional iterator. It is specifically designed to efficiently iterate over arrays of any dimension. In the example, we pass the nd array to np.ndIterator inside a for loop. For each iteration, the variable x contains one element of the array, which is then printed. Notice that the output is a sequence of numbers from 1 to 8. Even though the original array is three-dimensional, ndIterator automatically visits every element one at a time, without requiring nested loops. Without ndIterator, iterating through a three-dimensional array would require 3 nested for loops, making the code longer and more difficult to read. The ndIterator function simplifies this process and makes the code cleaner and easier to maintain. In this slide, we'll learn how to iterate through a NumPy array while simultaneously retrieving both the index and the corresponding value of each element. Previously, we used np.ndIterate to access every element in an array. However, np.ndIterate only returns the values and does not provide their positions within the array. To obtain both the index and the value, NumPy provides the np.ndEnumerator function. The name stands for n-dimensional enumerate, meaning it works with arrays of any number of dimensions. In this example, we create a one-dimensional NumPy array containing the values 1, 2, 3, 5, 6, and 7. We then use a for loop together with np.ndEnumerator. During each iteration, the variable index stores the index of the current element, while the variable x stores the corresponding value. As shown in the output, the function returns pairs such as 0, 1, 1, 2, 2, 3, and so on. Notice that the index is displayed as a tuple. Even for a one-dimensional array, NumPy represents the index as a tuple, so that the same function can be used consistently with two-dimensional, three-dimensional, and higher-dimensional arrays. The np.ndEnumerator function is especially useful when you need both the location and the value of an element. It is commonly used in data preprocessing, debugging, matrix operations, and machine learning applications, where decisions depend on both the position and the data stored at that position. In this slide, we'll learn how to combine 2 or more NumPy arrays using the np.concatenate function. Concatenation simply means joining arrays together to create a larger array. This operation is frequently used when data comes from multiple sources and needs to be combined before analysis or machine learning. Let's begin with the first example. Here, we create 2 one-dimensional arrays named R1 and R2. The np.concatenate function joins these arrays end-to-end, producing a single one-dimensional array that contains all the elements from both arrays. Notice that the original order of the elements is preserved. Next, let's look at a two-dimensional example. We create 2 matrices, each having 2 rows and 2 columns. This time, we use the axis parameter. When we specify axis equals 1, NumPy joins the arrays horizontally, which means the columns are combined. The number of rows must be the same in both arrays for this operation to work correctly. If we had used axis equals 0 instead, the arrays would be joined vertically by adding more rows. In that case, the number of columns in both arrays must be the same. The axis parameter is one of the most important concepts in NumPy. In general, axis equals 0 represents operations performed along rows, while axis equals 1 represents operations performed along columns. The np.concatenate function is widely used in data preprocessing, feature engineering, image processing, and machine learning, whenever multiple datasets or arrays need to be combined into a single structure. In the next section, we'll explore additional NumPy functions for joining and manipulating arrays efficiently. In this slide, we'll learn how to combine multiple NumPy arrays using the np.stack function. Unlike np.concatenate, which joins arrays along an existing axis, np.stack creates a completely new axis in the resulting array. In other words, it increases the number of dimensions of the output array. In this example, we have 2 one-dimensional arrays.
When we call np.stack with axis equals 1, numpy places the corresponding elements from both arrays side by side, creating a two-dimensional array. Notice the output. Each row now contains one element from the first array and the corresponding element from the second array. This operation is useful whenever related data needs to be grouped together. The axis parameter determines where the new dimension is inserted. Different axis values produce different arrangements of the data. Array stacking is commonly used in feature engineering, dataset preparation, image processing, and machine learning whenever multiple arrays need to be combined while preserving their relationship. Horizontal stacking joins arrays from left to right. For one-dimensional arrays, this is very similar to concatenation because the elements of the second array are simply appended after the first array. In this example, two one-dimensional arrays are combined to produce a single array containing all the elements. The output shows that the values from the first array are followed immediately by the values from the second array. When working with two-dimensional arrays, np.hstack joins the arrays column by column. Therefore, the number of rows in both arrays must be the same. Horizontal stacking is commonly used when combining additional features or variables into an existing dataset before performing data analysis or machine learning.
Vertical stacking is useful when combining multiple observations, records, or samples into a dataset, where each row represents one data instance. As the name suggests, vertical stacking combines arrays one below another. In this example, two one-dimensional arrays are stacked vertically to produce a two-dimensional array. Each original array becomes one complete row in the new matrix. As you can see in the output, the first row contains the elements of the first array, while the second row contains the elements of the second array. This function is widely used while preparing training datasets for machine learning models. Unlike horizontal and vertical stacking, depth stacking joins arrays along the third dimension, also known as the depth axis. In this example, two one-dimensional arrays are combined to form a three-dimensional array. Notice the output carefully. Each corresponding pair of elements is grouped together in the third dimension, instead of being placed side by side or one below another. Although three-dimensional arrays may seem unusual at first, they are extensively used in computer vision, image processing, medical imaging, scientific simulations, and deep learning. For example, a color image is represented as a three-dimensional array, where the third dimension stores the red, green, and blue color channels.
In this slide, we'll learn how to divide a numpy array into multiple smaller arrays using the np.arraySplit function. So far, we've seen how to join arrays together using functions such as concatenate and stack. Sometimes, however, we need to perform the opposite operation by breaking a large array into smaller parts. This is where np.arraySplit becomes useful. In the first example, we create a one-dimensional array containing the numbers 1 through 6. We then call np.arraySplit and specify that the array should be divided into 3 sections. Since the array contains 6 elements, NumPy creates 3 equal-sized arrays, each containing 2 elements. The output shows the 3 resulting arrays, 1, 2, 3, 4, and 5, 6. In the second example, we attempt to divide the same 6-element array into 4 sections. Since 6 cannot be divided equally into 4 parts, NumPy distributes the extra elements as evenly as possible. As a result, the first 2 arrays contain 2 elements each, while the remaining 2 arrays contain 1 element each. One important advantage of np.arraySplit is that it works even when the array cannot be divided equally. Unlike the np.split function, it does not generate an error when equal division is impossible. Instead, it automatically creates nearly equal-sized subarrays. Splitting arrays is commonly used in machine learning, data preprocessing, batch processing, and cross-validation, where large datasets are divided into smaller portions for efficient processing or model training.
In this slide, we'll learn how to search for elements in a NumPy array using the np.where function. The np.where function returns the index positions of all elements that satisfy a specified condition. Instead of returning the values themselves, it tells us where those values are located within the array. Let's look at the first example. We create a one-dimensional array containing the values 1, 2, 3, 4, 5, 4, and 4. We then search for the value 5 by writing np.where arr equals 5. The output is array, 4, 4, which means the value 5 is located at index position 4. Remember that NumPy uses zero-based indexing, so counting starts from index 0.
In the second example, instead of searching for a specific value, we search for all even numbers using the condition ARR%2 equals 0. The modulo operator returns the remainder after division by 2, so any element with a remainder of 0 is an even number. The output displays the indices of all even numbers present in the array. Notice that np.where can evaluate conditions and return every matching position, making it much more powerful than searching for a single value. This function is widely used in data preprocessing, filtering datasets, identifying missing or invalid values, selecting records that satisfy certain conditions, and preparing data for machine learning algorithms. As you continue learning NumPy, you'll find that np.where is one of the most frequently used functions because it provides a simple and efficient way to locate data based on logical conditions.
In this slide, we'll learn how to use the np.searchSorted function to determine where a value should be inserted into a sorted array. Unlike np.where, which searches for existing values, np.searchSorted tells us the position where a new value can be inserted while maintaining the sorted order of the array. This function assumes that the input array is already sorted in ascending order. Let's begin with the first example. We have a sorted array containing the values 6, 7, 8, and 9. We use the statement np.searchSorted r7 side equals right. Here, the parameter side equals right tells NumPy to return the insertion position immediately after any existing occurrence of the value 7. Since 7 is already present at index 1, the function returns index 2, indicating that a new 7 should be inserted after the existing one. If we had used side equals left, or omitted the side parameter, the returned position would be index 1, which is before the existing value 7. In the second example, instead of searching for a single value, we search for multiple values, 2, 4, and 6, in a sorted array containing 1, 3, 5, and 7. The function returns the positions 1, 2, 3. This means that 2 should be inserted at index 1, 4 at index 2, and 6 at index 3 to preserve the sorted order of the array. One important advantage of np.searchSorted is that it can efficiently process multiple values in a single function call, making it much faster than checking each value individually. This function is widely used in binary search algorithms, data insertion, time series analysis, database indexing, and machine learning applications, where maintaining sorted data is important.
In this slide, we'll learn how to sort NumPy arrays using the np.sort function. Sorting is one of the most common operations in data analysis and machine learning. Organizing data in a meaningful order makes it easier to search, analyze, and visualize information. The np.sort function returns a new array with the elements arranged in ascending order. By default, it does not modify the original array unless the sorted result is assigned back to the same variable. Let's begin with the first example. We create a one-dimensional array containing the values 3, 2, 0, and 1. When we call np.sort ARR, NumPy arranges the numbers in ascending order, producing the output 0, 1, 2, and 3. The second example demonstrates that np.sort can also sort arrays containing strings. Here, the strings are arranged in alphabetical order. Notice that the output changes from banana, cherry, apple, and donkey to apple, banana, cherry, and donkey. In the third example, we sort an array of Boolean values. Since NumPy internally treats false as 0 and true as 1, the sorted result places all false values before the true values. One important point to remember is that np.sort works with different data types, including integers, floating point numbers, strings, Boolean values, and multidimensional arrays. This makes it a versatile function for many scientific and machine learning applications. Sorting plays an important role in data preprocessing, statistical analysis, searching algorithms, ranking, filtering, and preparing datasets before training machine learning models.
In this slide, we'll learn the simplest and most efficient way to filter elements in a NumPy array using Boolean indexing. Filtering means selecting only those elements that satisfy a particular condition. This is one of the most powerful features of NumPy and is used extensively in data preprocessing and machine learning. In this example, we first create a NumPy array containing the values 41, 42, 43, and 44.
Next, we create a Boolean condition using the expression AR greater than 42. NumPy automatically compares every element of the array with the value 42. The comparison produces a Boolean array: false, false, true, true. Here, false indicates that the condition is not satisfied, while true indicates that it is. We then use this Boolean array as an index by writing ARR filter. NumPy returns only the elements whose corresponding Boolean value is true. Therefore, the output becomes 43 and 44. Notice that we never use a loop. NumPy performs the comparison on the entire array at once, making the code shorter, easier to read, and significantly faster. Boolean indexing is the preferred approach in NumPy because it is optimized internally and works efficiently even with very large datasets. In this slide, we'll perform the same filtering operation, but this time using a traditional Python loop. We again begin with the same NumPy array, containing the values 41, 42, 43, and 44. Instead of letting NumPy perform the comparison automatically, we first create an empty list called filter array. Next, we iterate through every element of the array using a for loop. For each element, we check whether it is greater than 42. If the condition is satisfied, we append true to the filter list. Otherwise, we append false. After the loop completes, the filter list contains the Boolean values: false, false, true, true. We then use this Boolean list to index the original array, producing the filtered result containing only 43 and 44. Although this method gives exactly the same output as the previous example, it requires more code and performs the comparison one element at a time. For small arrays, the difference is not noticeable, but for large datasets, NumPy's built-in Boolean indexing is much faster because the operations are implemented in optimized C code. Understanding this loop-based approach is still valuable because it helps explain what NumPy is doing internally when it creates a Boolean mask automatically. In this slide, we'll learn how to filter only the even numbers from a NumPy array using Boolean indexing. We begin by creating an array containing the values 1 through 7. To determine whether a number is even, we use the modulo operator. The expression ARR modulo 2 equals 0 checks each element of the array and returns true if the element is divisible by 2 and false otherwise. NumPy performs this comparison on every element simultaneously, producing a Boolean array. We then use this Boolean array to index the original array. Only the elements corresponding to true are selected, giving the output 2, 4, and 6. Then, we learn how to add new elements to an existing NumPy array using the np.append function. We begin by creating a one-dimensional array containing the values 1, 8, 3, 3, 5, and 7. We first print the original array so we can compare it with the updated result. Next, we use the np.append function to add a new value, in this case the number 7, to the end of the array. The syntax is np.append original array, value to add. One important point to remember is that NumPy arrays have a fixed size. Therefore, np.append does not modify the original array in place. Instead, it creates a completely new array containing both the original elements and the newly appended value. That's why we assign the result back to the variable ARR. Finally, we print the updated array and observe that the new value has been added to the end. The np.append function is useful when constructing arrays dynamically, although for large datasets it is generally more efficient to collect data in a Python list first and convert it to a NumPy array only after all elements have been added. In this slide, we'll learn how to find the unique values present in a NumPy array using the np.unique function. We begin by creating a two-dimensional NumPy array containing several repeated values. Notice that the value 11 appears multiple times, and the value 12 is also repeated throughout the array. When working with real-world datasets, duplicate values are very common. Sometimes we need to identify only the distinct values that exist in the data. To accomplish this, NumPy provides the np.unique function. Since no axis is specified, NumPy treats the entire array as one collection of values. It removes all duplicate values and returns only the unique elements in sorted order. The output contains the values 11, 12, 13, and 16. Each value appears only once, regardless of how many times it occurred in the original array. The np.unique function is widely used during data preprocessing to identify distinct categories, remove duplicate values, analyze datasets, and prepare data before applying machine learning algorithms. We can also find how np.unique can be used to find unique rows or unique columns by specifying the access parameter. In this slide, we'll learn how to swap two columns in a two-dimensional numpy array. We begin by creating a 4x3 numpy array using the np.arrange function. The numbers from 0 to 11 are generated automatically and then reshaped into 4 rows and 3 columns. We first print the original array so we can compare it with the modified result after swapping. Next, we define a function called swapArray. This function accepts 3 parameters: the array itself, the index of the first column, and the index of the second column. Inside the function, we use NumPy's advanced indexing to exchange the 2 columns in a single statement. The expression selects all rows while choosing only the specified columns. The 2 selected columns are then assigned in reverse order, effectively swapping their positions. We then call the function by passing the array along with the column indices 0 and 1, which swaps the first and second columns. Finally, we print the updated array and observe that only the selected columns have exchanged positions, while the remaining column remains unchanged. Column swapping is commonly used in data preprocessing, feature engineering, image processing, and matrix manipulation when rearranging data before performing further analysis or training machine learning models. NumPy's advanced indexing allows us to perform this operation efficiently without writing loops, making the code both concise and fast. In this slide, we'll learn how to remove unnecessary leading and trailing zeros from a NumPy array using the np.trimZeros function. We begin by creating a one-dimensional array that contains several zeros at both the beginning and the end, along with meaningful values in the middle. In many real-world applications, such as signal processing, sensor data analysis, and time series data, leading or trailing zeros often represent unused or padded values that are not needed for further analysis. The np.trimZeros function provides a simple way to remove these extra zeros. In the first example, we call the function without specifying the optional trim parameter. By default, NumPy removes both the leading and trailing zeros, while preserving any zeros that appear between other values. Notice that the zeros inside the array remain unchanged because they are part of the actual data. Next, we specify the parameter f, which stands for front. This removes only the leading zeros and leaves the trailing zeros untouched. Finally, we specify the parameter b, which stands for back. This removes only the trailing zeros while keeping the leading zeros. It is important to remember that np.trimZeros only removes zeros at the beginning or the end of a one-dimensional array. Any zeros that occur in the middle of the array are considered valid data and are never removed. This function is particularly useful when cleaning datasets before visualization, numerical computation, or machine learning, where unnecessary padding values should be discarded without affecting the actual data.
Okay, guys. Hope you have enjoyed the session, as I did. And see you next time for another session on pandas. Wish you a good time learning data science and machine learning. 21.